Welcome everyone to Shadow the Scientists. My name is Raja Guhathakurta. I'm a professor at the University of California, Santa Cruz, and we started Shadow the Scientists um, at the height of the pandemic in 2020 when telescopes were shut down. Physical access to mountaintops became difficult, if not impossible, and even university campuses where we would go to use remote observing rooms to use telescopes, even those became inaccessible because we didn't really understand how the coronavirus was spreading at that time. So a mode of observing was started called pajama mode observing, where we could sit at home and use telescopes. And it's really during that time. In pajama mode started in the summer of 2020. In November 2020, I had this idea that, all of a sudden the playing field is sort of level in that nobody's on the mountaintop. Quite literally, our playing field was level. Everyone was in the plains, not in the mountains. And in a real sense, the scientists using the telescope were physically as close or as far away from the telescope as any random eavesdropper. All you had to do is get on a Zoom call. Now, of course, that is an oversimplification. The scientists who were sitting in their homes had access to the software that you're seeing on your screen that you could use to control the telescope. And that was not available to others who were eavesdropping. At any rate, I didn't know how boring or interesting this would be for people to see, sort of the authenticity of how research works. It's sometimes slow. You're taking long exposures, and normally you're checking your email during that time or chit-chatting about something unrelated to the experiment. I didn't know how boring or interesting this would be. And to my surprise, the people I invited to this were super engaged. They were asking all kinds of technical questions about detectors and telescopes and about the astronomy questions. So that was a single session in November 2020, but things really took off in February of 2021. I was working with a colleague, and she and I got a bunch of students involved. And in particular, there were indigenous students from different parts of the US who were starting to, thanks to her, she was able to connect these students through Zoom to various astronomy sessions. We had a different name for this, but later we changed the name to Shadow the Scientists. We got a grant to support this initiative. And really, a lot of the credit for this work goes to Jamaica Marshall, who's the STS coordinator. I know, Steph, she worked with you to set this up. Jamaica would be the person introducing the session normally, and she lives on the Big Island, but she's taking a well-deserved break for the 4th of July, and she's actually traveling. So here I am on the Big Island trying to do my best Jamaica Marshall impersonation. And so I'm doing a terrible job so far, but Jamaica is really the mover and shaker behind all of this. And thanks to Jamaica, Shadow the Scientist has moved beyond astronomy. I know tonight's an astronomy session, and our very first set of sessions for the first year or so were astronomy, and most of them were within my research group. So the first thing that happened was it moved beyond my research group to other astronomers. And the next thing, and this has been really very much Jamaica's work, is we've gone from astronomy to also including stem cell biology. And there's a real parallel there. In astronomy today, you don't look through telescopes. You see an image on a computer screen. The same is true for powerful microscopes. You don't put your eye to an eyepiece anymore. You get images showing up on a computer screen. And if you're running Zoom on that computer screen, you can share what the scientist is seeing with participants in a Shadow the Scientist session. So in a way, it was very easy, seamless to go from astronomy to stem cell biology. We're looking at, instead of looking at something very large, very far away, you're looking at something small, close by, but you still need magnification to see these things. But the interfaces were very similar because the scientists are sitting at computers in both of these cases. Then Jamaica expanded to other subjects, and that involved a difference in format. We went to tropical forest ecology, where we're actually tracking scientists out in the forest. The person who's running Zoom is using an iPad, and they're talking to people. It's not just about screen sharing. No, in fact, it's entirely about live video of people doing research. So we went to tropical forest ecology as the third subject after astronomy and stem cell biology. And then the fourth subject was also in the nature of field work, where we were tracking oceanographers on research vessels, on ships that were out in international waters. And again, a person was running around the ship to various laboratories on the ship as they were drilling into the ocean floor with a goal of learning about the Earth's climate history. Sort of deep time through the nature of the samples collected from beneath the ocean floor. A million years into the Earth's past, or a few million years into the Earth's past. So it's so far, Shadow the Scientist is in these four subjects: astronomy, stem cell biology, tropical forest ecology, and oceanography/paleoclimatology. We're about to expand into two more fields. The fifth field is going to be the study of volcanoes, volcanology, based on scientists here in Mauna Loa on the Big Island of Hawaii. And the fifth topic is actually astronomy related, but not astronomy. We are going to be shadowing the engineers who are in the process of building the giant Magellan telescope. So it's about engineering. And it's a different kind of deep time there, because I know astronomy is, of course, about the history of the universe and deep time. But in the case of telescope engineering, when you're building something on the scale of the Giant Magellan Telescope or the LHC or LIGO, they're often talking about engineering projects that take not months or years, but decades from conception to, to the experiment actually working. So we think it'll be interesting for young people to see engineering projects on that scale. More than the astronomy, really engineering on that scale, on that kind of budget, on that kind of time scale, that kind of size of team. So that will be based both in Pasadena in the GMT labs, as well as in Chile, where the telescope is going to be located in the Andean foothills. Anyway, that was a very long introduction of Shadow the Scientist, and normally it's much shorter, and Jamaica gives this introduction. But with that, I'll hand it to you, Steph. And I know I may be running into your next task on the science side.
Oh, that's okay. I think we'll be in good shape. All we're planning to do is do a move on the slit and then start this again. But if I have to pay attention to that in a minute, I'll just mute myself and come back.
No problem, Steph. I also was going to say that I think this is your first time being an STS host, so welcome, and thank you for agreeing to do this. But you bring another first, which is, I think this is the first time we have two telescopes being used at the same time. You have Keck I and Keck II in use at the same time. LRIS on Keck I and NIRSPEC on Keck II, right? So that's a first for us too.
That's exciting. Yeah, we're really excited about this program. First, I'll introduce myself, and then Christina, you can introduce yourself. So I'm Steph Sallum. I'm an associate professor at UC Irvine. I'm an observational astronomer and an instrumentalist. So as an observer, I'm interested in trying to understand how planets form and evolve. And so that means taking pictures of distant young stars where we think planets are actively forming. It also means characterizing known objects that have planetary masses, which is what we're doing tonight. And as an instrumentalist, I also work on building next generation instruments for telescopes like Keck, so that we can do even better science related to planets and planet formation in the coming decade or so. So yeah, I'll leave it at that. Christina, do you want to take over?
Yeah, sure. Hi, I'm Christina. I'm a fourth year PhD student at UC Irvine. I'm also a very frequent Keck observer, but I work on a different project. I've been imaging protoplanetary disks with a hope to find a planetary companion. But so far I've been mainly characterizing disk structure. And I use a technique called aperture masking interferometry, or non-redundant masking, to look at for planets in very small separations, so almost on the scale of like solar system. And yeah, so I have experience working with Keck, but this is very different. So I'm learning a lot right now, looking at all the different GUIs for LRIS and NIRSPEC. This is very fascinating.
Yeah, it's busy. It is a busy program. Yeah, and so I can talk a little bit about that. But first, let me just take a look at where we are. Okay, we're still taking one image, so I don't think we need to do anything. I'm just going to check in with somebody else on the team and make sure we don't have to do anything for another couple of minutes. Josh, after the blue exposure ends, are we going to do a slip move -15 and then start again, do you think?
Yeah, that's what I was gonna do.
Okay, cool.
Are you're on the other call now?
Yeah, I am, but we can we can talk about stuff.
Okay, I'm just gonna keep sort of nodding along the slate back and forth.
Okay.
So whenever you're available, we can decide if we want to make a change.
Okay. Cool. Okay. So now I am back and focusing on this. Raja mentioned that we're using both telescopes at the same time. So this program is aimed at getting simultaneous observations of a forming planetary mass object. So the science goal here is to do a really good job characterizing an object that is something like 10 times as massive as Jupiter. So we call it a planetary mass object as opposed to a planet, because it's on the high end of what we would call planetary mass. And the reason why we need to use both telescopes is because we want to get simultaneous observations from the ultraviolet through the infrared. And so that means that we need to use one telescope to get the ultraviolet through the optical light and the other telescope to get the infrared light. What's going on with this object is that it's still actively forming. So when you form a star, you form it from a cloud of dust and gas that collapses. This object is a planetary mass object, so its formation mechanism is still a bit uncertain. But what we do know is that it's still accumulating gas and dust from its surroundings. And we can use observations of objects like this to inform how we search for forming planets. So because gas is falling onto this planetary mass object, and the planetary mass object is very heavy, the gas gets really hot when it falls onto it. So what that means is that this gas that's made mostly of hydrogen is going to get shocked, and the hydrogen is going to lose electrons, so it'll become ionized. And then when it recombines, when the electrons fall back down onto the hydrogen nuclei, you see all this light being emitted because of the change in energy states of the atoms. So all of that is just the physics behind the different features that we're looking for in these observations, which is very bright emission in the blue and in the UV, and then some very narrow peaks throughout the optical and the infrared. And that's because of the wavelengths of light that hydrogen emits. So the way that we try to detect that is with spectroscopy. So what we do is we take the light from our object, and we spread it out in wavelength using something like a prism. And then we record an image that shows us how bright the object is versus wavelength. So that's actually what you're seeing here is a spectrum of the star that this planetary mass object orbits. So here, over here, our detector isn't very sensitive. This is very far in the ultraviolet. And then we're increasing in wavelength over into blue light as you move all the way across. So this is the LRIS instrument. LRIS is what's giving us the UV
readout, please.
through the optical light. And you can actually see a little diagram of LRIS over here. So LRIS has two cameras, one for red light and one for blue. So light comes in, we put it through a slit to make a very narrow image, basically. And then it goes through some mirrors. And the red light goes to one camera that has one prism-like object in front of it, which is actually called a grating. So you can see the grating setting here. It disperses the light, so it spreads it out as a function of wavelength. And then the blue light goes to this other camera that has a prism-like object called a grism, which is kind of halfway between a grating and a prism. And you spread out your UV through blue light. So to control LRIS, you can change different settings related to the slit that you put in, the central wavelength that you're observing, different filters. We just have clear filters, so we're letting all of the light reach our detector in the red and the blue, and then different calibrations over here. And because we have two cameras, we actually have two different control windows for each, or for the two cameras. So this is the control software for the blue side, and the images that we're seeing from the blue camera. And then over here we have red. So similar GUI, you can see, you can set things like exposure time, number of exposures. It shows you whether it's currently sending light to the detector or if it's just reading out the pixels on the detector, which are over here. And again, this is your spectrum starting from close to blue over here on the left side, and then going through the red and close to the infrared on the right side. Just to complete the tour of all of the VNCs, this screen just shows you what object we're looking at. So this is the name of the object. It's called SR12. The primary, what we call the primary star, or the star that the planetary mass object is orbiting, is actually a pair of stars. So that's why it's called AB. And the planetary mass object is SR12C. So maybe I'll just pause there. That's a very quick tour of LRIS and a quick explanation of the science. I don't know if there are questions related to that. I see some stuff in the chat. Let's see.
There are a few questions in the chat, Steph. This is not polarized light.
Yes, that's right. This is not polarized light. This is just total intensity. That's a great question.
I know we were exchanging notes earlier, Christina and I, about Paschen and bracket series, and I just looked something up. Well, I knew that Paschen and bracket series involve transitions to and from the, well, Paschen series involves n=3 energy level. And if it's an upward transition, it's an absorption line. If it's a downward transition, it's an emission line. But the Paschen series always includes n=3 and some other higher level, 4, 5, 6, 7, etc. Bracket series, it's 4 and above. That is between 4 and some level above. So again, upward transition is absorption line, downward transition is an emission line. And then I was looking online to make sure I had these names correct. And I realized I didn't know. I knew about the Fun series, which is level 5 and above, but I didn't know about the Humphrey series. And it's actually spelled like that. That's not a, actually it auto-corrected. It's actually spelled Humphery.
Oh, funny. I didn't know that either.
Yeah, I'd never heard of this. So the Humphrey series is, let's see, I'm going to write this out So after Brackett comes Pfund, and they're named after scientists, of course, who discovered these in the laboratory, and all three of these, or all four of these, Paschen, Brackett, Pfund, and Humphrey, are in the infrared. And infrared spectroscopy, of course, came later. People first started with optical spectroscopy, and then they moved to the ultraviolet and infrared later. Partly because they didn't have devices to see the infrared. I guess photographic plates were very good at seeing optical light.
Yeah.
And it started with the eye, of course. It started with the human eye, not with any. And that, of course, was not sensitive to the ultraviolet. And
Right, or the infrared, yeah.
Let's see. I did have a question. I guess your brown dwarf is so close to the star that you expect that you have to model and subtract off the stellar spectrum in order to be able to see the brown dwarf. Is that?
Yeah, that's right. That's right. So the separation is about,
Complete.
sorry, just letting the noise go by. The separation is about 9 arc seconds.
Oh, 9 arc seconds. Okay, so no, that's not bad. Okay.
Yeah, no, it's not so bad. I think the reason why we still have to do some modeling to disentangle the star and the planet, or the planetary mass object, is just that the star is so much brighter. That, like, some of the like wings of the stellar PSF are still present where the planet is. Yeah.
Gotcha. Now, I'm seeing in the upper panel
Complete.
SAO image LRIS blue, I'm seeing a second line.
Yeah.
Is that something? That's
So,
not 9 arc seconds, right?
yeah, let's see. So that's X of 292. No, yeah, so that's not, that's about 4 arc seconds. So we've seen this before in LRIS blue data, and we think that it might be a ghost or something like that.
Oh, not a background star or anything?
No, yeah. Yeah, because if I go over to the red, there are a lot more, there's a lot more skylines in the red, but if you look over here,
You don't see it.
yeah, you don't see it. And red and blue are flipped with respect to one another. So if we were going to see it in red, we'd expect it
Right
below. Yeah.
Got it.
Yeah. Yeah. We've seen artifacts like this in blue data before.
Gotcha.
Yeah.
And in the red, there is you can see the brown dwarf in the red, right? That's is that faint streak in the lower panel? Is that the brown dwarf? No.
No, it's actually at a much smaller separation than that. So I think that's just a nearby object that happened to fall on the slit, which is maybe off the top of the blue LRIS detector.
Gotcha.
Yeah, because it would be somewhere like up here.
Up there.
Yeah.
Gotcha. And of course, the PSF or the spectrum is the same all along the PSF. So could you use the half of the PSF that's further, that's on the wrong side, to reflect it and subtract it off? Or do you have to, that would be completely empirical, or do you have to do proper modeling of the, I don't know if I'm being clear.
No, I understand what you're saying. I think you mean with the blue, like with the blue ghost?
No, I meant just in general, when you're subtracting off the light of the star, could you use the half of the PSF that's away from the brown dwarf as a empirical model for what to subtract?
Oh, yes, I think we should be able to do that. The only issues there that I could imagine running into would be, if you weren't great at accounting for flat fielding that changed across the PSF. But no, yes, in principle, yeah, that we haven't had to do this kind of modeling before for this program. And so I have a feeling we're gonna have to get creative like that when we actually want to pull out the brown dwarf spectrum. Yeah.
And I imagine you can work in 1D, right? You can extract two halves and then work in 1D, because I imagine also that sometimes lines of constant wavelength don't exactly run along columns. And but if you have a full 2D wavelength solution and you extract top half, bottom half, and then subtract, hopefully. And I assume the brown dwarf spectrum looks very different, much lower temperature than the stars spectrum.
Yes. Yeah, that's right. Yeah. Yeah, and we do expect to see emission lines from the brown dwarf, and so that can also help us, you know, if we see line profiles that look like there are two objects there,
Gotcha.
that can help us locate it. Yeah.
Super cool.
And that's actually what I think Josh, who's running LRIS right now, is looking at. He's taking slices through the spectrum and looking at what the shape of the you know, PSF is at different locations.
Got it.
Yeah. Yeah, and he's looking in the wings to try to see if we can see any bumps because of the light from the brown dwarf.
I see emission line bumps.
Yeah, or even I'm not sure where.
Even continuum. Yeah, even continuum. I
Yeah,
guess.
that's right. It looks like right now he's looking at the continuum. If you can see the vertical green line in the SAO image window, yeah, where his mouse is, he's kind of moving that along the spectrum to try to find the trace from the brown dwarf. And I think he might see it. The place where he's drawing that line, if you kind of like squint at things above the star, there's like a very faint trace.
I think I can see it. Yeah, there's a faint trace.
Yeah,
I can see it.
yeah,
I mean, it's a horizontal trace, right? So,
yep, that's right.
you know, you can see it, especially between the night sky lines.
Yes, yeah, yep, that's right.
You can see it, you know, where the word histogram appears, the letters GRAM, there's a gap in the emission lines. I can sort of see it there.
Yeah, yeah. So I
I
think
don't know if
that.
you can yeah, sorry.
No, go ahead.
I was wondering if you can change the contrast on the SAO image. Does
Oh,
histogram equalization give you, actually, the word histogram should give you histogram equalization if you try
you're
that
right.
on this here.
All right, let me just give Josh a heads up that I'm going to do that.
Okay.
Josh, we were just talking about what you were doing, and it looks like there might be a trace like where you were mousing over before, huh?
On the right side?
Yeah, yeah.
Maybe, yeah. I mean, that one looks like it could be real. It's very faint.
Yeah. I'm gonna just put the stretch on histogram just for a second to see if that helps.
Yeah, I can't stretch this display with my mouse.
Oh,
That
No, I
wasn't
can't,
good.
like, just adjust the scaling with the mouse like you can in DS9.
yeah, I know what you're talking about. I don't know if I can. On histogram, there's like, I wonder if this, let me put this back on.
It looks like something there.
Oops, Max.
You were on log before. I can see something.
Yeah. So that's interesting.
Because it's on the upper side, it's not on the lower side.
Yeah, I am, Josh. Yeah.
Yeah, but I mean, that looks real, that thing, I think.
Yeah, I think so. I don't know.
And
Yeah.
it's very clearly not on the lower side. It's above the star, but not below.
Yeah, you're right. Yeah, so that's exciting. I think this means that if we stack the images.
It's in the right place too, right? It's like exactly 65 pixels away.
Yeah. Well, that's great.
That's promising. Yeah, I was thinking maybe we want to integrate longer in each
frame.
in each position.
Yeah, okay.
Because we need to build up signal anyways.
Yeah, I know you're right. And
Readout complete.
I assume we're just gonna sit on this for like basically the rest of the night. So
I think so. And I think that we hit the limit before handover and that we can just go back to one white dwarf before handover.
when is handover?
Like 12:20 Hawaii time.
Well, it says we have 4.5 hours to limit.
Oh, right. The Keck I limits are in the
It's the NIRSPEC limit.
Yeah. No, I had it backwards. Yeah. Okay, great. So yeah, we can just stay here as long as we want.
So maybe I'll basically double the amount of time on source. We're doing like 15 minutes now, but we could go longer.
Yeah. You mean between?
Yeah,
Yeah, but yeah.
Were the limits you were talking about the Naismith deck limit?
Yeah, that's right.
That's far to the east on K1, right? It's
Yes,
been
yeah,
subject to
and on
dry zone.
K2, it's in the west, and so I
I'm
always,
so used to K2 and being on the west.
yep, me too. Yeah, Christina was saying that she's a frequent Keck user, and she's a NIRSPEC user, which means we're always thinking about the west limit.
Yeah, I'm a DMOS user. I'm always thinking about DMOS and ESI. I'm always thinking about the west limit.
Yep.
But we have some time on Osiris coming up, so I'll have to think about east limit.
Oh, cool. What's the Osiris program?
We are, this is LGSAO, and it'll be looking at the nuclear star cluster of the Triangulum galaxy M33.
Cool.
To understand like hemodynamics.
Okay. So you're getting like positions, velocities, and also metallicities or something like that?
Right. So that's right. Positions of basically individual stars in the
Okay.
nuclear star cluster, but yeah, positions and Doppler shifts
Okay.
and chemical composition.
Cool.
Yeah, we've tried to do this with Gemini, but there's a significant difference. I mean, difference in aperture, and of course, something like this goes like d to the 4. So, Keck versus Gemini should give us an advantage. And
Yeah.
and it's not the kind of science I normally do, so I'm excited about new direction.
That's cool. I can pull up the NIRSPEC VNCs and we can see what's going on over there.
That'd be great. Thank you. Thank you.
Okay, let's see. All right, here we are. Did that work? Can you see NIRSPEC now?
Yes.
Okay. Okay. So and I'm not gonna touch anything here because I'm not dialed into the NIRSPEC control room, so I'll just describe what's going on. So NIRSPEC can be operated in a very high spectral resolution mode. So this is another spectrograph. So you're dispersing the light across wavelength. NIRSPEC is an infrared spectrograph. It can operate between like 1 micron and 5 microns. We're using it right now in 2 to 4 micron mode. And this is one of the bracket lines that we're going after. So we're trying to observe this object in bracket alpha, which is at 4.05 microns. So the way that you do this at high resolution with NIRSPEC is you use what's called a shell mode. So this is where you use one prism to disperse the light at low resolution. And then you have a grating downstream of that, which is also a disperser, but rotated perpendicular. And so what that does, is it creates many kind of like rows of spectra, each of which is at high resolution and covers a narrow wavelength range. So that's actually what you're seeing in this NIRSPEC format simulator GUI right now. You can see in the graphic a little drawing of where all of the different wavelengths of light from 2.13 microns to 4.22 microns are going to show up. And the orange box that says 1 is actually the field of view of the NIRSPEC detector. So what you have to do when you're using NIRSPEC in this mode is configure the instrument so that you place the detector field of view over the wavelengths that you're interested in. So Raquel Martinez, who is running NIRSPEC, has done that so that the bracket alpha line at 4.05 microns falls basically right in the middle of the detector. And that is on the second from the top blue line over on the right-hand side, basically in the middle of the orange box. So this VNC shows you us setting things like the slit width, the filter that sets your wavelength range, and the positions of the dispersers that allow you to isolate the wavelengths that you're interested in. There are other GUIs here. Okay, so here you're seeing the actual detector image for NIRSPEC. And what's going on with this one is that Raquel has taken data at two slightly different positions on the sky and then differenced them. And so that's why it kind of looks fuzzy in these horizontal stripes, but then there are these kind of negative sharp lines. Those are negative traces from the exposure that Raquel is subtracting from the current one. It looks like she's currently on the primary star in the system based on
readout complete.
Based on the object name. But let's see if we can find out for sure. I'm gonna avoid her VNC so I don't mess with her mouse. So this is the telescope status window. Okay, so over here it says HIP 73200. So this is a calibrator star. So something that you need to do when you take spectroscopy of a science target is observe some reference whose spectrum you know very well. And by observing that spectrum, then you can do things like calibrate the flux of the object that you're actually interested in. So HIP 73200 is a bright star that has a spectral type A. And the reason why I use A stars is because their spectra are very well understood. It's easy to fit some model to it and then actually be able to go from counts on your detector to, physical units for your spectrum.
Exposure complete.
So let's see what else we have. So there's the NIRSPEC detector again. And then let me pull this up. So what SCAM is actually showing you a camera pointed at the slit in the spectrograph. And so here you can see that they're zooming in different ways on the image of the slit, but the diagonal dark line that you're seeing in the little thumbnail in the Ginga raw image, which is now actually in the big window, that diagonal line is the slit, and then you can see a negative image of the target, which is the calibrator star, which was just in the orange circle, and now it's moved off because the zoom has changed. So our goal with NIRSPEC is to observe bracket alpha and also, which is 4.05 microns, and also Paschen beta, which is 1.28 microns. And we want to combine that with UV continuum on LRIS, and also hydrogen lines in the optical and UV. So things like the Balmer series, basically.
CCD readout complete.
In particular, H alpha at 65, 63 angstroms, but then also some lines in the blue.
Exposure complete.
Steph, I had a question and a comment.
Yes.
Why is the slit at an angle like that? Not vertical.
Yes. So the slit, that we had been keeping the slit at an angle, and actually this looks like the correct one, so that we could put both the primary and the companion on the slit. And I think that Raquel has just kept it at that angle when she moved to the calibrator star.
Calibration star. That makes sense. Okay.
Yep.
Yeah.
Yeah, and that angle is 165 degrees relative to north. So you can see it's almost aligned north-south. So yeah, it's about 15 degrees away from north-south.
Readout complete.
Let's see. Is north up and east left? Oh, no. I see. North. I can see the compass rose in the big window. Okay. So it's actually north is I see the compass rose in cyan in the fanned out window in the upper left.
Yep.
Okay,
Yeah,
so it's
so
actually tilted clockwise relative to 15 degrees clockwise relative to northeast. That makes sense. 165.
Yep, that's right. Yeah. Yes.
And then I wanted to take a moment to talk about Eshell spectroscopy in general. I guess the step size between the Eshell, I guess, means steps in French, and
Yeah.
the gap between the steps, if that's d, then d is equal to the path difference, the path length difference between a light ray going off one element of the step versus the adjacent element. The path length difference at whatever angle is equal to n lambda.
Yep.
But you can trade off n and lambda. So as you go to different ends, you get different lambdas constructively interfering. So you basically spread out multiple orders, but they would have landed one on top of the other on the detector. So use a cross-dispersing prism in this case to spread out the orders. And that's why there's also a tilt, because within each order, it's not all the same wavelength. It's a range of wavelengths, and the prism moves it by different amounts. That's why you get that tilt between the orders, or tilt within an order, and the tilt, of course, changes as you get from as you move to from shorter to longer wavelength.
Yep.
I think of an Eshell spectrograph as reading sentences in a textbook, except in this case you read from left to right and then you read up, not down. But it's yeah. Yes, it is indeed sort of double spectroscopy, as Aparajita pointed out. Yeah. So Aparajita is actually one of my research students. He's based in India, and he does a lot of spectroscopy.
Hello.
And he's on his way to the US in a few days to be part of the SIP program this summer as a mentor.
Awesome.
Exposure.
I asked my interns to drop by, attend this event. So yeah, I thought I should, hop on and check it. I don't think any of them are here, but I've been enjoying this discussion myself.
And this is being recorded, so they can also watch afterwards.
Yes, yes.
Well, thanks for dialing in.
It's let's see, what time is it? It is 12:45 in California right now, which means it's 1:15 in the afternoon in India. It's 12 and a half hours from California.
Okay.
Oh, Steph, here's another
It
tip.
is.
India is a half-hour time zone. It's not an integer. And I thought that was bad, except I found out a few months ago that Nepal is 15 minutes ahead of India. 15.
No way.
Yes,
No.
that is correct. There are quarter integer
20-minute time zones and
zones.
15-minute time
Yes.
zones. There are even 20-minute time zones. Yeah.
Yes.
Oh wow. Oh my gosh. I didn't know. So I knew that India was 30 minutes shifted compared to us because we have telecons with people at IIA for scales.
Of course, yeah. You're working.
But I had no clue. I didn't know about the 15 minutes.
No, it's crazy. And often this is about political sovereignty more than anything else, wanting to distinguish oneself from an oppressive neighbor. Yeah, I mean, another great geographic anomaly is the state of Alaska. You know how the international dateline has a funny kink in it, so that all the islands that belong to Alaska are on one side of the dateline.
That makes sense.
But technically, you do that just to give them put them in the same time zone, but you don't change their geographic longitude. That of course is what it is. So Alaska is the easternmost and the westernmost state in the US because of this.
Oh, whoa.
And it's the northernmost,
Weird.
it's really weird, right? It has basically 180 west and 180 east longitudes. Oh, 179.999. They're both part of Alaska. In spite of that funny kink in the dateline. Actually, that funny kink in the dateline is related to that.
Right. That makes sense.
And of course, I'm sitting close to the southernmost point in the United States. So Hawaii has the southernmost point. Of the 4 cardinal directions, none of them are in the mainland.
Yeah, how funny. That's so, I've never, that's something that's obvious once you think about it, but you don't think about it.
The obvious state that comes to mind is Maine, being the
Right.
eastern,
Read out,
but actually not.
please.
I think Kiribati has the most obvious kink in the dateline, right?
I see.
If I remember correctly. I think they are the nation that celebrates New Year first.
Yeah.
Pretty sure. Yes.
Yeah. They jut out to the east.
Yes.
And whereas the Alaskan one juts to the west.
Yes. I get the Polynesian countries confused, but Kiribati is the one that is so easy to remember because, I remember that's the one with the weird time zone and it stretches very far to the east.
I see. So one of the things we're starting to do in Shadow the Scientist and more generally CREST is starting to reach out to. That's why I'm here in Hawaii, Steph and Aparajita. I'm actually here to promote our outreach. I'm giving a talk in Waimea on Sunday. I'm not here to observe. I'm actually here for outreach. And we're trying to go beyond Hawaii to the Pacific Islands more generally. French Polynesia, South Pacific. French Polynesia is in the news right now because the Paris Olympics are on, and the Olympic surfing competition is actually in French Polynesia because France, right? Paris.
Yes.
Oh, funny.
Oh, and yeah, I mean, France is in the news in Polynesia for other reasons too.
Exposure complete.
Yeah, there was political upheaval in the Kanaki Islands.
I see.
I mean, what the indigenous people call the Kanaki Islands. And yeah, there's demand for independence, and they held a referendum. But basically, what it came down to is that overall, the island didn't want to secede, but it was mostly the indigenous people who did want to secede, and it was mostly the people who, trace their ancestry to elsewhere who did not want to secede. So, yeah, it is a tense political situation right now.
Steph and Christina, I know we are well past your 1 hour. Should
awesome.
we let me know, and I'm happy to stop the recording at some point, and I'll we'd say goodbye to the Shadow the Scientist participants and let you get on with the rest of your night. But just you give me the word, and we'll call it an end to the.
Read out, please.
Okay, yeah. I mean, I'm happy to stick around for a bit longer if people. I mean, the way that these things tend to go is that they're really exciting when you're getting set up, and then you kind of just get in a groove and you're taking exposures. Every like 10-15 minutes we'll be doing it for the next 2.5 hours. So we can stick around if people have extra questions or if people want to see any of the GUIs again. Otherwise,
I'll keep the recording on then, Stefan. Boring is good in this game, right? When everything is going smoothly. one of our most exciting STS sessions was when the ESI guider broke and we had to improvise in real time. And honestly, people commented about how they enjoyed seeing the scrambling. What do you do? How do you adapt? We didn't want to lose the night, but we were able to adapt, and we got comments afterwards that that's not something you usually get to see. Sort of, quote unquote, something fails, but it's not a catastrophic enough. People have seen catastrophic failures where the weather is so bad or the instrument has some terrible glitch, but this is sort of an intermediate level failure when you can do something, but not what you set out to do. And the process of scrambling and figuring out what to do this is exactly what these things are about, is very much about people and process. And
that makes sense. That's cool. It's always stressful when you have to troubleshoot things when you're observing, but at least in this instance, people got to get a feel for how it actually goes a lot of the time.
Everyone went dead silent because it was exciting. They were just watching, what was happening. Yeah.
What did you end up doing?
So this was an RLRI program where we're supposed to look at very faint RLRI. And of course, you need to guide because these are like half-hour to, several series of half-hour exposures.
ECG readout, please.
Do you need to make a switch?
No, sorry. I'll mute myself so that those don't.
No, it's perfectly fine. No, it's good that you have the sound on because it really, this is part of being an astronomer. These sounds are important.
Yeah.
No, so we looked at a bright RLRI all night, and we monitored it. So of course RLRI, we were there to measure their. We had discovered some really distant RLRI, and we're trying to measure their velocities with spectra. But these are strange beasts. They pulse, and their photospheres can move relative to their center of mass at speeds approaching 100 kilometers per second. So their instantaneous velocity is different from their center of mass velocity. The instantaneous photospheric velocity can be different from their center of mass velocity, which is the center of mass velocity doesn't change. At least not on human lifetimes. These things accelerate, of course, but that's negligible compared to photospheric. So we have to monitor these. We have to correct for these things. When you measure an RLRI, you measure it at some phase, and you have to correct to center of mass. So this gave us a great opportunity to monitor a single star for a large fraction of the night and empirically see how its photospheric velocity is changing with time.
That's cool.
Got some good out of it.
How significant were the changes during the night in the photospheric velocity?
Tens of kilometers per second.
Okay.
Because we were able to sit on this object for something like 5 or 6 hours. And that's a significant fraction of a typical phase. That's about half a typical phase. Typical RLRI periods are half a day. So we sat around for 6 hours.
Cool.
And so, again, there are really cool things that happen. You see, we were working in the optical, so you're seeing the Balmer lines only, but the H-alpha line gets double valued at some point because there's a shock that runs through the star and all kinds of madness happens. The H-alpha line shows 2 absorption lines with an emission line in between, in just some phases of the pulsation. These things look like EKGs. So when they go up rapidly in brightness, it's that time that a shock goes through the.
Okay, that makes sense.
It doesn't affect the higher order Balmer lines as much.
Readout, please.
H-alpha is particularly affected by this.
Okay.
Yeah, it's crazy to think that. These are horizontal brown stars. They're not as big as the sun, but still, they're, they're not tiny. They're not white dwarf size. White dwarfs are, even white dwarfs, they're the size of the Earth, right? And these things are much bigger than white dwarfs. They're horizontal brown stars. to think that something that size can pulse
Yeah.
by a significant amount in like half a day is crazy. I mean, there's no
Yeah.
wonder that the photosphere moves at tens of kilometers per second.
Yeah, it's really funny because you learn about all these pulsations, when you take classes about stars. But sometimes you don't stop and think about the fact that like the stellar atmosphere is moving like at 10 kilometers a second is really fast.
Yes, really fast. And the thing sloshes, right? So it sloshes. So not all of the stars moving at the same speed. So these different Balmer lines are formed at different depths
Right.
in the stellar atmosphere. So of course they have different velocity profiles.
Right.
And it's a really cool way of probing a star in a way that you often don't get to.
Yeah.
Yeah, I've become really fond of these things.
That's cool.
We've found the spectroscopy can't quite reach these stars, but we've now found the galaxy's most distant stars.
Oh, that's right. Yeah, you've mentioned this before.
Yeah, so the paper came out a couple of months ago, out in April, but the most distant stars are 300 kiloparsecs from us. 300. So 40% of the distance to Andromeda. Just to give you a sense of scale. We're not looking in the direction of Andromeda, but it's 40% of that distance. And we are finding these, other surveys are finding these in other directions of the sky. So I've been joking that, our property line is getting further and further away. And, this property were in Silicon Valley, I'd be rich. This is very good property. But the prediction from computer simulations is at some point you should see a downturn in the power law slope of rho versus log rho log r.
Okay, I was wondering.
Yeah, so far it looks like a power law, but with no break.
Okay, interesting.
Aparajita was asking a question. I wonder if there are currents at specific latitudes in stellar atmospheres as we...
GCD readout complete.
Well, you certainly see this in planets, in Jupiter.
Right, I'd expect that. Yeah.
Yeah, and actually, to push, I guess, not all the way to stars, but close to stars, people have made observations of what look like zonal winds on brown dwarfs. So they're not, those aren't stars, but they're somewhere kind of between planets and stars. And people have mapped surfaces of those. Yeah.
Like physically map
Yeah,
them, but
that's really interesting because I didn't know that you could even do that with brown dwarfs, with them being so far away.
Yeah,
so these are nearby brown dwarfs and AO and IFU?
It is so not mapping in the imaging sense, but what they do is they they take time resolved spectra of brown dwarfs. And then fit models to the spectra, like with, changes across the surface. So you have like a spectrally dispersed light curve, and then you're saying, what must the surface of my brown dwarf look like as a function of time to match this?
Got you.
Yeah.
So this is time resolved spectroscopy, rotating brown dwarf. And
yeah, that's right. Yep.
It's super interesting. This reminds me of something years ago when I was when I was a grad student at Princeton. I didn't know this professor at the time. I later became his colleague. Steve Vogt came to Princeton to give a colloquium. And this is long before Doppler, the Doppler method, long before exoplanets was a word, right? Long before. We're talking about the 80s.
Readout, please.
So he was studying star spots, and he was doing time resolved spectroscopy with high res, well, not high res, with the Hamilton spectrograph at Lick. This is before Keck. Keck I was built in 1982. First light was in 1992. We're talking about good 5 years before that.
Wow.
So Steve, I still remember this, had this model of a star in which he had an artificial model of a star in which he had written his own last name in star spots, like VOGT written on the star, rotating. And he was trying to show us that you could reconstruct to the extent to which you could reconstruct. I still remember that it was a star with vote written on it.
That's cool.
Now, Prajita, later, this person became a pioneer in the Doppler method for detecting exoplanets, and of course, they were beaten to the punch by Mayer and Kellers in Switzerland, but they'd been studying 51 Peg for years, and they were able to verify that their data had the same planet signal in it.
Yeah.
That's really cool.
I've seen people do things like that with deformable mirrors when they're like first you get a new deformable mirror and you're just demonstrating that you can do something with it. I've seen people put patterns on the actuators to make, like simple pictures or like a letter or something.
Gotcha.
Yeah. Let's see. So it looks like on LRIS, where the red side is finished reading out, blue is probably still, yeah, so blue is still exposing. When blue finishes, Josh will probably send another move on the slit. So what we're doing with these slit move commands is we're shifting the light up and down on the detector so that we can easily do background subtraction by differencing images. So Josh has been sending these commands to move the spectra up and down with this slit move word that you can see in the terminal over here.
That moves the target along the slit.
Yeah, that's right.
Exposure complete.
I'll take a peek at NIRSPEC. Okay, so on NIRSPEC, Raquel has switched over to J-band now. And if you look at this GUI, the format simulator, you can see it doesn't look like the Echelle GUI anymore. Like there's just one bar from 1.14 to 1.37 microns. And that's because she's in low spectral resolution mode. So we're not using Echelle spectroscopy anymore. We're just dispersing the light with a grating.
So you replace do you replace the Echelle grating with a mirror and use the prism?
Readout complete.
I do think that's how it works.
I'm noticing the spectrum runs vertically instead of nearly horizontal before.
Yeah.
That's what ESI does. That's its low resolution mode, is you replace the Echelle grating with a mirror and just use the cross disperser.
Yeah. Yep. Yeah, so that's good that they're going after J-band. Let's see. Okay, they're on the science target. So you can see they're on SR12. Oh, and maybe they have a trace from the companion. So if you look at the Ginga image, the bright, they're zooming in. So the bright star is the star is the bright trace, rather, where she's mousing over right now. And then there's the faint line right of it. And so that looks like it could be the companion.
Which faint line to the right of it? I'm not sure I see it.
It's almost vertical. Sorry, I don't want to use my mouse because I'll mess up her.
Sure.
But if you look in the big window in Ginga, there's the bright line that is curved and running almost vertical. And then you see the light blue text that says cuts 0. and there's like a line underneath it that's almost horizontal.
Yeah, I see that.
The horizontal line is going through a fainter, similarly curved trace.
Got you. Can barely see the word cut zero.
Yeah, it's hard to make out over the skylines. Yeah.
I'm colorblind also, so that doesn't
Oh,
help.
oh gosh. Yeah, I would imagine that would make it much more difficult.
You don't mean the trace that's to the right of the bright star. That's the other random other star, right?
Oh no, that's the one that I mean.
Oh, that's the one you mean. Okay.
Yep,
So it's about like a third of the way from the bright star to the right edge.
Yes, that's right.
Got it. Got it. I see it. I see that loud and clear. Yeah. And
Yeah.
and Steph, a quick question near the top and bottom of the bright star. I see the pinching. Is that just telluric absorption?
Oh, that's a good question.
Readout complete.
I think so, yes. Yeah, but it is, you know what, it's kind of right, if you look at the red box, it's kind of right on the edge of what I think is like the spectral range of that mode. So it could just be the edge of the filter.
Of the blocking filter, right?
Yeah,
Okay.
yeah.
Because my understanding is the J, H, and K bands are sort of limited by telluric absorption anyway.
Yeah, that's right. Yeah, and I don't actually know I mean, well, I don't know off the top of my head the cutoffs for the filter specifically. Like you can see the wavelengths here, 1.143 to 1.375.
I see. Yeah, that's too short to be all of the J band. The J band isn't it more? Yeah, it's quite a bit broader than that. 1 point. I think this is J, right? You said J.
Yes, yep,
Okay.
that's right.
This is the blue edge of J because J center is 1.2.
Yeah, yep, yeah, and it's more wider than
Quite a bit wider than.
yeah, that's right.
This looks like it's just 0.05 microns wide.
Yeah.
1.14 to 1.1.
1.37 here. Let me.
That's tiny. Yeah. 1.37 to
1.143 to I think it was 1.375. It's under the sleep wrapper.
Got you. Okay, yeah. Oh no. So this could be all of the J band then.
Yeah,
1.2 would be in the middle of that.
yeah. I feel like here I'm just gonna look up the NIRSPEC J-band filter because I think we can find that easily.
Sorry to be asking questions in the middle of your.
No, it's good. It's good. I don't get to. So when we run this program, Raquel is always on NIRSPEC and I'm always on LRIS, and this is actually the most time I've gotten to spend with the NIRSPEC GUIs, which is fun. The J-band, I think we're just barely tighter than the nominal J-band width. It's like 1.128 to 1.40.
Oh, okay. Okay.
CCD readout complete.
And the reason I was asking about telluric is you can sort of see the molecular bandhead structure of molecules in the Earth's atmosphere. You wouldn't get that from a blocking filter, right? So,
no, yeah, it would be weird behavior in a filter, like not something you would want.
yeah, exactly.
Yeah.
Whereas I'm so used to seeing this in the telluric. You see what I mean? There's sort of this ringing pattern on the upper side. You can see that. On the lower side, I don't. But
yeah, you can see maybe one line at the very bottom, but not.
Yeah, I see one line at the bottom, but I see
Yeah.
a series of lines. Looks like a band head there.
Yep.
Fraunhofer would have been very happy. You know how he thought the A band was in the sun, of course, and he called it A because it's the first letter in the alphabet, and then he struck out with the second letter of the alphabet too.
Yeah, no, I love that history when when you talk about like the calcium H and K lines.
They're part of that same sequence. Sodium D.
Yep.
The G band for iron, right?
Mm.
All of that, yeah. I don't think there's an I and a J because they were considered pseudo. they're not, he was using, I don't know, started with the A and B, so he clearly was using vowels.
Right.
Yeah.
Yeah, I wonder.
I don't know about the C band, for example.
Mm,
I know about sodium D, but
yeah.
I know about ING. Yeah.
Well, I think in a few minutes I should probably give Josh a break from running LRIS.
Okay. I'll hit I'll hit stop on the recording.
Okay.
This will make its way after Jamaica's had chance to edit it. Oh wow, that's beautiful.
Oh, great timing. Yeah, we can talk. Let's talk about this before we.
Of course. And I can see that the negative version of the fainter thing is right on the edge of the star, right?
Yeah,
The
yeah,
positive
and
edge of the
yeah. That's one of the tough things about sending these offsets is that you don't always know how close you are to like putting your negative image.
Readout complete.
oh,
But it is
beautiful.
just barely offset.
Just barely offset, yeah.
Wow, these look great. This is great.
Beautiful.
Yes.
Sorry. Oh, please go ahead, Steph.
No. Go ahead.
I was going to ask what this is. Why do we have this positive and negative pattern here of the traces?
Yeah. So what we're showing here is the difference between two images. And the reason why you can see positive and negative is because between the two images, Raquel has sent an offset to move the objects along the slit. So what that does is basically, you're still dispersing the light from the two objects, but they move spatially on the detector. And so she's shifted one image to the right compared to the other image. And so the reason why we do it is because then what you can do is you can subtract the two images and remove the sky.
Exposure.
The night sky lines are beautifully removed. That's
Yeah.
so cool. I see some vertical, I see some horizontal striping. Is that detector?
Yeah, that looks like those look like the readout channels. Like they have widths that I would expect for the readout channels.
The night sky lines run at some tilt. They don't run horizontally, right?
That's right.
In fact, Aparajita has been playing a lot with 2D spectra, a lot with DMOS 2D spectra. So this is when you're talking about two images, it's 2D spectra, one subtracted from the other.
That's right.
Yeah, I wish we had this good physical suppression in DMOS.
Yeah.
Like, it's amazing.
A bit more
it's
variable.
amazing. Yeah. Yeah.
Sorry, Raquel is trying to log on. And I'm gonna see if she can. She might be busy, but I'll give her a minute.
Yeah. So
Yeah.
is she logging on to this STS session?
Yeah. I
Okay,
think
I'll keep an eye out if I
Okay.
see her. And Aparajita, what you do is you extract the positive and the negative, so you're not losing any signal. Yeah, you do a positive extraction of the positive
Right.
version
Right.
and a negative version from this image itself, and then you co-add the two. You flip one sign and then you co-add the two.
Right. God, this is all so, I don't know, this is all so clever. I have never really seen I've never really seen somebody observe with visual spectroscopy. Yeah, I wasn't familiar with it. And this is amazing. I love this.
So high res is in a shell. That's what the EN high res.
Right. That's
then
the NIRSPEC. Yes.
ESI is also the EN ESI. That's the not the EN NIRSPEC, right? It's near infrared spectrograph, but the EN NIRS, I guess, is a shell spectrograph.
Complete.
Hi, Raquel.
Hello, finally made it. Sorry.
No, we were just admiring your J-band images. They look great.
Oh yeah, finally
Beautiful.
photons.
Raquel, if you want to take a minute to introduce yourself, we're actually recording this session, so you'll go down in posterity as an STS superstar.
Hello everyone, I'm Raquel Martinez. I'm a postdoc at UC Irvine, working with Steph. Yeah, interested in how planets form and trying to observe them while they're actively forming.
Thank you. You know, the artist in me sees these 2D spectra. I see a pencil point at the bottom. Looks like a pencil.
Totally. Maybe like a quill even with the little lines at the top.
You know, in the old days, people had these two-sided things where you had different nibs at different ends of the pen, or different pencil points at different ends of the pencil.
Yeah, I can see it.
Exactly like that.
Readout complete.
What? I hadn't heard that. Aparajita has a tidbit here. I recently learned that helium was first observed from India during a solar eclipse. I had no idea.
Yes, that is true. I think it was, properly confirmed later, but the very first observation was in fact from Andhra Pradesh. I think it was French or English astronomers.
I knew that helium was discovered in the sun, and that's why it has its name, named
Yes,
after Helios.
yes, it's named after the sun. Yes.
Okay, Steph, we were going to end the session. I'm going to go ahead and do that.
Okay.
And this will make its way after Jamaica's editing on both on our STS website, but also in our STS YouTube channel.
Sounds great. And thanks again for having us. It was really fun to do this.
Well, thank you. I mean, it's really, without STS host, none of this would happen. So thank you. Thank you for agreeing to do this. And looking forward to many more sessions with you guys.
Yeah, us too.
All right.
Glad I got to join for a little bit. Bye everyone.
Yeah, thank you, Raquel.
Thanks, Raquel. Thanks, Christina. Thanks,
Yeah,
Steph.
yeah,
Thanks,
thank you,
Aparajita.
Christina.